Hey there, so here we have 6.2, which is a continuation of 6.1. It's again the molar heat of reaction, but in this case we're going to be looking at a neutralization. So again we have two different components. We have an environment and we have a reaction. In this case it's a neutralization. Again what we're doing, we're looking at the temperature of the environment as an indicator of what the reaction itself is doing. Is it absorbing heat or is it releasing heat? Let's pretend it's absorbing heat. Well, it's taking heat away from the environment, which means that the temperature of the environment should cool down. We're drawing heat away. Now, in the case of an exothermic neutralization, so the energy is being released into the environment, that means the thermometer should pick up more heat and the temperature should go up. So that's basically the principle we're applying. Again, we're using Q equals MC delta T for the environment. So based on how much water I have, specific heat capacity of the water, and its variation of temperature, I can determine how much energy the water or the environment gained or lost. Now, because normally these situations or reactions occur in an isolated environment, we can say that whatever energy the environment absorbed or released, well, it should be equivalent to the amount of energy that is involved in the reaction. So we have again plus Q is equal to minus delta H, or minus Q is equal to plus delta H depending on the case. The small difference here is to obtain the number of moles that react in a neutralization. We're not dissolving something, so we're not looking at a mass. If you remember from before, we had a mass of salt that was dissolved. So to find the number of moles, we do mass over molar mass and we determine how many moles of salt were dissolved. In this case, we're not dissolving something, we're neutralizing something. And we know that an acid or a base normally have a concentration. It's not pure. So to obtain the number of moles that were neutralized, I need to know the concentration of my acid or base as well as the volume used. So N is equal to C times V, or if you prefer, C is equal to N over V. That's the one you learned last year. That's how I will determine how many moles of acid or base were neutralized. So that's the small difference here. To find N, we use a slightly different formula. Now the ratio delta H over N still gives me the delta H molar for the neutralization in this case. So if we look at the equations needed to solve a problem like this, they're very similar to last time. The only difference is here, we're going to have a mass of what? A mass of water, right? But if you think about it for a second, my water comes from where? It comes from the water within the acidic solution as well as the basic solution, right? Because we're neutralizing something, we actually need two solutions to achieve that. So there's water here, there's water here. So my mass here will be the sum of both this and this. So I have to add up my volumes to determine the mass of water there is. You're going to say, but Miss, in a solution, there's not only water, there's a little bit of acid, a little bit of base. Yes, exactly. There is a little bit of acid and a little bit of base. It doesn't make enough difference if I say I have 100 ml, let's say, of an acidic solution. Well, really, I have 99.99999 or whatever milliliters of water, and the rest is the acid. Same thing for the base. So it really doesn't make a difference if I use 100 ml or if I use 99.99999 as a volume or as a mass for the water. It's basically one and the same. So we're not going to bother really separating the solute from the solvent in this story. We're just going to take the volume of the acidic solution plus the volume of the basic solution and consider that that's the volume of water present in the system. Now this remains true in this case. Whatever Q or the water absorbs was released by the neutralization or vice versa. If the water released energy, well, that means the neutralization gained it. For the number of moles, like I said, the difference is we're not going to do M over M. We're going to do concentration of the acid or the base times its volume. So this here is really going to be for the substance that is designated in the question. So they'll always say find the delta H molar of neutralization of the acid or of the base. So let's pretend they say delta H molar of the acid. So that means you're going to work with the information for the acid only. So the mass is a combination of acid and base, but this here is only for one or the other. And it's the same thing here because this comes from here. Okay? So let's apply this to an example. Okay, so in a calorimeter, you completely neutralize 100 ml of an aqueous solution of sodium hydroxide at 0.5 mole per liter by adding 100 ml of hydrochloric acid solution at 0.5 mole per liter. The very first thing I'm going to do, I'm going to separate again into columns my information. So I have my water, which is my environment, and I have my neutralization, which is really my reaction. Okay, so I'm using, for the mass, 100 milliliters of an aqueous solution of sodium hydroxide and 100 ml of hydrochloric acid. So in total I have 200 ml or 200 grams. I know that my specific heat is 4.19 joules per gram degrees Celsius. Now for the neutralization side, to find my N, I'll need to know the concentration of my substance, the volume of my substance. We'll get back to this after. Okay, the initial temperature of the solutions before being mixed is 22.5. So I know this is going to go from my environment. So Ti is 22.5. So the water within my solution is at 22.5. The highest temperature obtained during the neutralization, so that should be my TF, is 25.9 degrees Celsius. Calculate the molar heat of neutralization of sodium hydroxide. I now know that the concentration I need to use is the one of sodium hydroxide. So here they tell you that it's 0.5 mole per liter, so 0.5 mole per liter. My volume is 100 ml. Now, because my concentration is in mole per liter, I'm going to convert this right away to a number of liters, an amount of liters, so it's 0.1. I will need here to find a delta H and finally a delta H molar. That's what they're asking for. All right, so what can I do first? I can calculate my N. So C is equal to N over V, or N is equal to C times V, which gives me 0.05 mole. Now I'm stuck because I don't have either of these amounts, but what I can do is here solve for Q. So my Q will be MC times delta T, which gives me 2,849.2 joules. So now if I transfer this over here, I will have negative 2,849.2 joules. Now I know that delta H molar is always expressed in kilojoules, so I will convert this right away into negative 2.8492 kilojoules. And now with my moles and my delta H, I'll do delta H over N. That will give me my delta H molar, which is negative 56.984 kilojoules. So this is exothermic. So there you go. That's it for chapter 6. See you next time for chapter 7.